All right, so yesterday we finished up by talking about these three properties. So these are properties that we can use to take logarithms that are together and split them apart, or we can take ones that are split apart and combine them. Okay, so the way we did it yesterday is we took ones and we split them. So now the last thing we're going to look at is how do we take ones that are split and put them back together. So it's all the steps that we did yesterday, but in reverse. So instead of saying separate into multiple logarithms, it's now going to say combine into a single logarithm. And it says to put things back as exponents. So the other direction said basically do not leave powers in the answer. Put them in front as factors. This is the reverse. So now we are going to put powers back. All right. So what number there would go back on something as an exponent? The 4. Okay, so that's the first step. So we're going to have log base A of, and the 4 is going to go back. So I could put it as 3 to the 4th, but I can also just do that out so I don't have to worry about it later. I think we just had a homework question with that. What's 3 to the 4th power? 81. Yep. So put the 4 back as an exponent on the 3 and simplify that. Okay, so now we still have to express it as a single log. Right now that's 2. When I recombine those into one log, what's going to be my base? Yeah. The base is going to stay exactly the same as what you have right now. Log base A. And with the 2 logs, we have addition. What does addition turn into when you recombine it into 1? It turns into multiplication. What's going to be on the left side of the
7.
multiplication? Yep. And on the right side? 81. And then if there is any arithmetic you need to do, then we do that out. If one of these was an x, then we wouldn't be able to do it out. Like if it was an x and an 81, we'd just be 81x. But that's a 7 and an 81, so we can multiply them together. So it's the log, don't forget your base A, of 567. Any question on recombining that into a single log? All right, let's try this one. Before you write that, I'm just going to change that. So 2/3 ln 8 minus the ln of 3 to the 4th minus 71. Well, let's start with this one. What's going to happen in that first one?
2/3 is going to go back to
The 2/3 is going to do what?
go back to the 8 as an exponent.
Go back to the 8 as an exponent. Okay, so we'll figure that out in a second. Now, inside that second log, we have a calculation. We can just do that, so we don't have to keep writing it that way. What's 3 to the 4th? Yeah. So it's really 81 minus 71 inside there. What's 81 minus 71? 10. Okay. So try to make my 1s look like 1s, and my L's look like L's. Okay, so we have the ln of 8 to the 2/3. Let's type that in and just see what that comes out to. 8 to the 2/3. So that comes out to 4. So we have ln 4 minus ln 10. What's the base on each of those, even though it's not written? E. Okay, there's no E, but we understand that it's there. Okay. When we recombine these, we're going to have a single ln, and we have subtraction in that problem. How does subtraction combine back together? It turns into what?
Division.
Turns into division. So we're going to have division, and what's going to be in the top? 4, and the bottom, 10. And just like a regular fraction, if you can reduce it, we should. What does 4/10 reduce to? 2/5. So that's how you would take the original problem and then combine it back together into one. Any question on either of those two? A or B? All right. Anyone feel like they need to see one more of that kind of problem? Let's do, well, you know what? Let me do one I asked you about right at the end yesterday. Let's say we had log, make this bigger so you can see it. Log base 3 of, let's do, square root of x plus log base 3 of 7. Okay. First, I guess the first question you should ask is, are they the same base? Yeah, if they're not the same base, then you can't combine them. Right? They have to be the same base. So base 3, base 3. So when we recombine them into a single log, what's going to be my base? 3. It stays the same. Now we've got addition. When you recombine addition, what does that turn into?
Multiplication.
Multiplication. So we're going to multiply this times this. So 7. It doesn't matter the order, right? I'm going to do 7 times the square root of x. The reason I put the 7 in front is because if I do this, to me that looks confusing. I can't really tell, is the 7 under the square root or not? If you put it in front, then it eliminates that problem. It's not under it. Now, directions said to basically express powers in your final answer. There is a power that's hidden here that we need to fix. What has a power on it, but it's hidden? Yeah?
X. Yeah.
The x has a power on it. If we rewrite that the way that they want it, what power would x have? What is it? 1/2. Yep. That is x to the 1/2. Okay, so if you did this problem and you got to that step, you'd get partial credit. But if the directions specifically said your answer should have an exponent, you haven't written it clearly with the exponent there. In the bottom one you have. Okay. Any question on that one? Okay. All right, so last thing we're going to take a look at for this week is 5.5. So we are skipping part 2 of 5.4, and we're doing 5.5. So we've looked at some things with logs. Okay, we've looked at what they look like. We haven't graphed any by hand, but we did look at a graph on the calculator and saw that it was like a mirror image of an exponential. It was a reflection. So we looked at that. We also looked at properties of how to combine them, split them, and then we had a few other properties before that. There were 4 of them. All of those would be good things if you're going to make a reference sheet to put those on it. But the last thing we haven't looked at is how do we type in a log in the calculator that's not one of the bases that it has buttons for, and how do we do transformations? So what are the 2 bases that we've talked about that the calculator has buttons for? Yep. Yes. The calculator has a button. If you want to do a base 10 log, you press the button to the left of the 7. So if you want the log of 74 and you want to do base 10, that's how you do it. Now if you want to do the log of 74 and you want to do base E, that's how you do it. So what do we do when it's not a 10 and it's not an E? Well, we're going to use what's called the change of base formula. So the change of base formula allows you to plug in a log that's not base 10 or base 8. I'm going to show you a way to do it that will work on any calculator that has a log button. Some other calculators might have fancier ways to do it, but not every calculator has that. So I'm going to show you a way that works on any calculator with a log button. Okay, there's actually two ways to do it. That is the first way. So if you want to take a log base b of x, where the b does not have to be a base we know how to do. It could be a 4, a 5, 6. Could even be a decimal, 2.7. Okay, b can be any number you want, but remember the domain of logs. It can't be 0 and it can't be negative. It can't be that. So it can be any number that's greater than 0. Same with x. X can be any number greater than 0. Can't be negative, can't be 0. The way that you type that in on the calculator is using the common log button. So you could take the common log of the argument and divide by the common log of the base. And it does matter which one goes where. Since the base, think of the base as being lower. When you write it on line paper, the base is lower, so the b goes in the bottom. The x is higher, so it goes in the top. Right? And the other way you can do it is, instead of doing the common log of the argument and dividing by the common log of the base, you can do the natural log of the argument and divide by the natural log of the base. And it comes out exactly the same. Okay, so let's look at an example. Log base 3 of 8. So first of all, when would you see something like that? This kind of thing would come up if you were solving this problem. When you were trying to solve for a variable that's in the exponent, a lot of times the answer is not going to come out nice. Okay. 3 to what power gives you 8? Well, if you do 3 to the second, how much is that? 9. That's too big. All right, now let's go down. What's 3 to the first? 3. Well, now that's too small. So the answer here is somewhere between 1 and 2. How would you get the exact answer? You would change this to log form. What's your base in that problem? 3. Logarithm always equals what kind of number?
Exponent.
The exponent. And what's the thing that is by itself? That's the argument. So the 8 is the argument. So solving this is how you get the answer for x right there. Okay, so let's see how we do it. We can take the log of the top and divide by the log of the bottom. Okay, let's do that out, and then let's plug it in for x and see if 3 to that number gives us 8. Let's take the log of 8. Make sure you close the parenthesis, and then divide by log 3. Doesn't matter if you close the parenthesis there, because you don't have anything else you're typing in. So that's in line with what we expected. It is between 1 and 2. Now let's check it. 3 raised to the 1.892789. I typed in a lot of decimals for accuracy. And it basically gave me 8. It's not exact because I rounded it. So now we just solved for that one. Now if you didn't want to do it with the log button, you could do it the same way with the ln button. You can't mix them. You can't use a log in the top and an ln in the bottom. No. You either use log and log, or you use ln and ln. Okay. And let's type it in that way and see what you get. ln 8 divided by ln 3. 1.8927, same answer. So that's how you type in a log that doesn't have a base of 10 or e. You have to type it in as a fraction. Okay, any question on that? All right, now let's look at a graph of that. Okay. First, is that a base 10 or a base e log? Is it one of the two? No. Then we can't type that in the way it's written. Can somebody give me one way that I can rewrite that so that I have something I can put in y1? Yep.
ln x divided by ln 3.
Sure. That's one way to do it. You can type it in as ln x divided by ln 3. Or you could have done log x over log 3 with base 10. All right, so let's put that in. When I type this in, what am I going to have to use as I type it in? But I didn't have to write it down when I did it on paper. Right, I'm going to have to put parentheses. Because when you plus ln, it's going to open a parenthesis for you. If you don't close it right now, it will come out wrong. Okay. So close it to indicate you are done with that argument. And then divided by, and now we're starting a new argument, ln 3. You don't have to close the 3. I like to close it. I close it. All right, let's do zoom 6. All right, let's look at sketch. And that's not really a good sketch. Why not? What's the graph not really showing that we said logarithms have? The asymptote. Right? Logarithms have what kind of asymptote? Vertical. It's not supposed to look like it just starts at -2. How far down does that supposed to look like it goes? Infinite. It's supposed to look like it goes down forever. And if I zoom in, well, first, does everyone agree it looks like it's starting at -2?
Yeah.
Okay. Well, if I zoom in there, where does it look like it's starting now? Now it looks like it's -3. So the calculator, it can't draw it because it's getting almost vertical there, and it doesn't know what to do when it gets that steep. So it really should look like that. Is it ever reaching the y-axis? No, because that's an asymptote. All right. So now, knowing that it never reaches it, that should help us find the domain. What's the domain for that? Think about how far left and right it goes.
0 to infinity.
The domain is 0 to infinity, including or not including 0? Not including 0. And of course, never including infinity. So that's the domain. 0 to infinity. And they also want the range. Okay, so range is up and down. What's going to be the range of that graph? Right, it's going to go down forever. And it is going to go up forever extremely slow. Right? It's as flat as it can possibly be without being flat. It just barely goes up, especially as you go further and further to the right. So range, all real numbers. And just to kind of give you an idea again of how slow it goes up, if you set x all the way to like 50,000, it still probably won't go off the screen on the y. It's going to be close. No, I'm good. So even when you get to 50,000 on the x-axis, it still hasn't even gone above 10. It's still under 10. So that's going up really, really slow. And remember, this part should come down forever. Any question on the change of base formula? Okay. All right, so transformations. So transformations are going to work exactly the same as every function that we've studied all year. So I'll write them all again. As always, there's a certain order to them, and the order you want to follow is A, B, C, and then D. Okay. A and B have something in common because they are inside the argument. Does anybody remember the direction that A and B is going to do stuff?
Horizontal.
A and B are always horizontal. Yep. Now, one's a stretch, one's a shift. Let's start with A. When you add or subtract, is that the horizontal stretch or the horizontal shift? That's the horizontal shift. And positive would move it to the left, and negative to the right. All right. So A is the horizontal shift. What about B? That's the horizontal stretch. And is it backwards or is it normal? It's backwards. So if you had something like log 3x, okay, I just got rid of everything else, just focusing on B. You might think, oh, that's a big number in front of x, it's going to make it bigger. No, it's actually going to make it smaller. So this would be a horizontal stretch by 1/3. If you did something like log 1/2 x, that would make it bigger. 1/2 would make it twice as big. Okay. And we've written that many, many, many times. Any question or anything more that people want me to talk about with the stretch? Okay, so that's A and B. They're inside the function. C and D are on the outside. Because they're on the outside, what direction are C and D going to do stuff to? That's going to be your vertical. Yep. So let's start with C. Is C the vertical stretch or the shift? It's the stretch. Anything that's multiplying is always a stretch. That's why B and C are stretches. And that one is not backwards. If you want to write that, you can. But if you had something like 2 log x, that is a vertical stretch by a factor of 2. It does make it twice as tall, right? Or stretch it twice as much. Okay. So it's not backwards. And how about D? That's your vertical shift. Yep. So vertical shift. And positive would move the graph in which direction? Up, and negative would move it down. Yeah, so vertical is nothing with vertical is ever backwards. It's the horizontal that's always backwards. Okay, so that gives you 4 transformations, A, B, C, D. What are the other 2 types of transformations that can happen? So what does that cause the graph to do, though? Yeah. Yes, we can get reflections. So I'll just put those down here. If B is negative, what kind of reflection is that? Horizontal or a vertical? It's horizontal because B is in the inside. B is always horizontal stuff. So that's a horizontal reflection. And if C is negative, what kind of reflection is that? That's vertical, yeah, because C has to do with vertical, so that's vertical. So the other way of saying a horizontal reflection is you can say a horizontal reflection is over the y-axis. A vertical reflection is when you flip up to down. That's vertical. That's over the x-axis. So you could say it either way. But that's your 6 transformations. Horizontal shift. B can give you horizontal stretch, horizontal reflection. C is vertical stretch, vertical reflection, and D is your vertical shift. So I would definitely have some type of chart like that for logarithms and exponentials, because we did the same chart on Monday too. But that's definitely going to be on the test. Which way does something move? Okay. All right, so let's look at this one. How can log, first thing is whenever you're comparing two logarithms, they need to have the same base. If they don't have the same base, then you're not going to be able to compare them. Okay. All right, so how can log base 3 of negative x be graphed from log base 3 of x? I'm asking, what do you need to do to the original to turn it into that? All right, and then once we do that, we'll find the domain, the range, asymptotes, all that stuff. First, how many transformations would it take to turn what's in the red box into what's in the blue box?
One.
Yeah, it's just one. Okay, there's only one transformation. What is the only transformation that you would need to do there?
Reflection.
Yep, what kind of reflection?
Horizontal.
Yep, the only thing is there's a negative, think of it as like a -1 in the B spot. So that's a horizontal reflection. It's not a stretch. To be a stretch, it has to be a number besides 1. Okay, but it's a 1. So horizontal reflection. Or if you want to say it this way, reflect over horizontal is y-axis. You could say it that way too. Okay, so you got the transformation. What else do they want? Find the domain, the range, and the vertical asymptotes. All right, well, let's make a picture of that. Okay, because it's not base 10, I can't type it in the way I would like to. So how am I going to type in log base 3 of negative x? I'm going to have to use a fraction.
Log x divided by log 3.
Log negative x
Negative x, sorry.
divided by log 3. Okay, we can do zoom 6. And that should make sense because normally a log function curves to the right. You've reflected it. So now it's going to curve to the left. So let's put that there. Let's make it a little smaller. And again, what's it not really showing really well? Yeah, it's not showing the asymptote at all. So that should be coming down. Just like that. Okay. That keeps going down. That keeps going that way. Okay, so now let's find the domain. The domain here has changed from what it normally is. What's the farthest left that this graph is going to go?
Infinity.
Negative. Negative infinity. And what's the farthest right?
0.
It goes right up to, but does it include 0? No. Okay, so the important thing there is when you do a transformation, you can affect the domain. Now let's look at the range. How far up and how far down is that blue graph going to go? Yep. Yeah, it's going to be negative infinity to infinity. It's going to go up forever as you head to the left, and it's going to go down forever at that vertical asymptote. So you can never change the range. All right? Any log function always has a range from negative infinity to infinity. It doesn't matter if you flip it, stretch it, shift it. You can't change that. All right? And the vertical asymptote. When you write a vertical asymptote, it has to be an equation. When you're writing a vertical line, what letter is by itself on the left? Yes. So it has to be x equals. And now, basically just tell me where that dotted line would be. What number does it go through? 0. X equals 0 is the vertical asymptote. Did that change by reflecting it compared to what it would have been if we didn't reflect it? No. Reflecting it doesn't change the asymptote because the original would look something like that. The only thing that would change the asymptote is if you do a horizontal shift. Okay, you got to do some kind of shift left and right to change the asymptote. All right, so we've got domain, range, and vertical asymptotes, and we got the sketch. Okay. Any questions on those? Let's try another one where we list transformations, but let's just add a little bit more in there. I want to know how this can be obtained from that. I don't want the domain and the range and all that, just the transformations. Well, first of all, does what I have written match the pattern in this red box? No, it doesn't match it exactly. Something's not quite the way it should be. What doesn't match there?
3.
Right. How should inside the parentheses be written? Right. The x should be first. So how should we rewrite that?
Negative x minus x plus 3.
It should be negative x plus 3. Right? You don't want to think of the 3 as even though the horizontal stretch is always supposed to be the first thing you see in parentheses, that's not written the right way. That 3 has nothing to do with a horizontal stretch. It has to do with the shift. That should be coming second. So it's not wrong in that order. It's just if you look at it that way, what's in this red box might not help you as much. So it should be like that. Okay, so now, how many transformations do we have? 4. 1, 2, 3, 4. Yep, we got 4 out of the 6. When you list them, we have to make sure we put them in the right order. So that's why I use the letters A, B, C, D. Start with A, and then work your way through each letter. Okay. Do we have a number in the spot for A? Yep, what's that number?
3.
It's a positive 3. And what does a positive 3 do? Shift left, how many? Okay. Do we have a number in the B spot that is not a 1? No. The number itself is still a 1, but what's in front of the number that's going to cause something to happen? The negative. So we got to talk about the negative. What does the negative do?
Reflection.
Yep, which kind?
Horizontal.
So that's a horizontal reflection. Okay, so we did B, go to C. Is there a number in the C spot?
Yes.
Yep. What number is in the spot for C? 4. And what's that going to do? Vertical stretch by 4 times as much. And now we go to the D. Is there a number in that spot? How about Chase right there?
Yeah.
Yep. What number is in that spot?
-5.
And what's that going to do?
Vertical shift down by 5.
Yep. So we're going to shift down 5. Okay. So those are the transformations and the order we should put them in. Any question on that? Okay. So now let's look at making a sketch. So when we are sketching log functions, a couple points that are helpful to find. Like if this was your log function, did something like this. Finding those two intercepts. Now, you are not guaranteed to always have both intercepts. One of those intercepts you will always have. Can anybody tell me which intercept you will always have?
X.
Yeah, you'll always have the x-intercept. Because remember, logs go up and down forever, and you never lift your pencil to draw them. So you are going to cross the x-axis somewhere, but maybe not the y. Okay. An example where you would not cross the y, right there. In that graph, you never cross the y-axis. Okay. But that's probably the most important thing we have to find when we're graphing, because once you know your vertical asymptote, then you have a line that the graph is going to bend away from. Okay? Whether it's going to bend away to the right or bend away to the left, we don't know. It depends if you flip it or not. But at least you have a line that it's going to bend away from. Okay, so you definitely want to find the vertical asymptote. All right, so let's go back to our diagram for a second. The vertical asymptote is a line that goes up and down forever. If you take a line that goes up and down forever, and say you shift it up 2 units, what would it look like if you shift it up 2 units, since it already goes up and down forever? It wouldn't change. Right? If something goes up and down forever and you shift it up a little bit, you wouldn't even notice. What about if something goes up and down forever and you stretch it and make it twice as tall? It would still be the same. So C and D have nothing to do with affecting the vertical asymptote. The only 2 letters here that could affect the vertical asymptote are A and B, the argument. So when we are trying to find what the new vertical asymptote is, we only have to look at the argument. And you set it equal to 0. That's how you find a new vertical asymptote. Set the argument equal to 0 and solve. C and D have nothing to do with the vertical asymptote, just A and D. If there was a horizontal asymptote, then yes, C and D would have something to do with that. But log functions don't have horizontal asymptotes. Okay, just a couple reminders of how you find each intercept. To find the x-intercept, you plug in 0 for the y. To find the y-intercept, you plug in 0 for the x. So sometimes it seems like it's kind of backwards, but that's how it works. So we're going to do both of these when we do a graph. And for logs, they're generally pretty easy to do. They're not. When you plug in 0 for the x and the y, you don't get a really complicated equation to solve. All right, so once you do that, you're probably going to have a couple points. You might have 2 once you know your intercepts. You're probably going to want to find at least 1 more. So then you can kind of get your curve. I would say you generally need about 3 or 4 points to graph a log. The other thing is we have to make sure we pick a point that's in the direction it curves. If you pick an x value over here and you try to work with it, you're going to get an imaginary answer because you're trying to find a point in the direction that it doesn't go. So that's not going to work. We got to pick a point in the direction that the graph is curving. Log functions always curve to the right unless you flip them. Okay? That's the only thing that can make it curve to the left, a horizontal reflection. we're going to look at this one. Okay, before we even really start to do anything, which way is this graph going to curve? To the right or to the left?
The right.
It's going to curve to the right. There's no horizontal reflection. So that means once you figure out what your vertical asymptote is, you need to pick points on that side of it. Don't pick anything on the left. It would come out, imaginary. Okay. All right. So let's start by finding the vertical asymptote. Set the argument equal to 0 and solve. All right. What's my argument there? 3x plus 5. A lot of stuff there, but the only thing that's the argument is 3x plus 5. Set that equal to 0, and now we're going to solve it, and that'll give me my new asymptote. It is going to move. It's not going to be where it normally is. What's my first step to solve that equation?
Minus 5.
Yeah, minus the 5. And my last step? Divide by 3. So that's negative 5/3 or negative 1 2/3. So about negative 1.6 repeating. Okay, let's sketch that right now. All right, so let's put in a vertical asymptote at negative 1.6. So somewhere. Perfect, but somewhere right around there. Okay. Next thing, let's see if we can find our intercepts. So let's start with the y-intercept. What do we fill in, and what letter do we fill it in for to get the y-intercept? Yep. You plug in 0 for x. Okay, well, let's do that. I'm going to just do it up here. Okay, y-intercept, plug in 0 for x. Right there. What's 3 times 0?
0.
And 0 plus 5?
5.
5. So this turns into a 5 if I do that. So I get log base 2 of 5. Now I have to type that in and get the answer. Is that a base 10 or a base e? Nope. Then I need to figure out how am I going to put that in on the calculator. Yeah, so yeah.
You do ln 5 over
Like that.
close bracket.
Like that. Yeah.
You ln 3x plus b.
No, that's just about right. So that's good, just about. But there's something.
Are
Yeah.
you missing a closing bracket?
Yeah. Where?
After the 5.
After the 5. Yes. So you need to do it like that. That is a different answer than what I had before. Okay. So the y-intercept is about 2.3. We're graphing, so I mean, how am I going to be accurate to the 100th? I can't. All right. So 2.3. So let's put the y-intercept. It's going to cross right about there. And that confirms the direction. It's curving to the right. It can never cross that dotted line, and I already have a point on the right of it. All right, now let's do the x-intercept. The x-intercept is when you plug in 0 for y. Well, where's the y? G of x, right? You might not see the letter y, but g of x means y. So fill in a 0 right there. So we get 0 equals log base 2 of 3x plus 5. Now let's change that. What format is this equation? Log. Let's change it to what? Exponential. Okay. What's my base there? 2. Logarithm always equals what kind of?
Exponent.
Yeah, logarithm always equals the exponent. And what goes by itself on the other side? The argument. 3x plus 5. Now we solve it. What's 2 to the 0 power? 1. Okay, what would we do next?
Minus 5.
Minus the 5. 1 minus 5 is negative 4. And divide by 3. There you go. So here, it's going to cross the x-axis at negative 4/3. That's negative 1 1/3. Okay, it's about negative 1.3. So that blue line is supposed to be negative 1.6. So it's a little bit before it. Now I would say let's do one more x value somewhere in that area. It's probably going to be up a little bit. But somewhere in that red circle would be a good x value to plug in to get one more point. So what would be a good x value?
7.
Yeah, you could do 7. Right. So if I plug in 7, what's 3 times 7? 21 plus 5? 26. So I have log base 2 of 26. So that's log 26 divided by log 2. I could have used that one. I didn't. So when x is 7, y is just under 5. Okay, so let's do that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, but just under it. And now draw your sketch. Kind of like that. All right. So we've got our vertical asymptote. I forgot to label it, but yeah, vertical asymptote is negative 5/3. What's my range? Yep, negative infinity to infinity. And my domain.
Not including 1.6 to infinity.
Right, it's everything from the vertical asymptote, I should say everything to the right of it. So where is the vertical asymptote exactly? I know it's about negative 1.6, but negative 5/3. So the domain is everything from negative 5/3, not including it, to infinity. And that's everything they wanted. Domain, range, and asymptotes. Okay, so any question how we did our sketch and found the asymptotes, the domain, and the range, and the intercepts. The intercepts were helpful just because it gave me 2 more points. The y-intercept is usually very quick. It's just a single calculation. Sometimes the x-intercept has like 3 steps in it, but it is all steps from like an algebra 1 kind of equation. Okay. Any questions on that? Okay. All right, so last thing. This is an application of an equation that uses a log, and this formula is used to find the intensity of an earthquake on the Richter scale. So if you've read something in the newspaper or watched the news, TV or whatever, and you see something about like a magnitude 5 earthquake, this is the formula for how they figure out that magnitude. Okay. So it has 3 letters, or 4 letters actually. So R is the magnitude. Okay, that's the number that everybody hears about. A is the amplitude of the ground motion in micrometers. So during an earthquake, the ground is going up and down. The amount that it moves up and down is A. And micrometers are very small. Okay, so depending on the earthquake, the higher A is, that's one of the factors that makes the earthquake worse, but not the only factor. Another factor that affects the earthquake is T. T is what we call the period of the wave. So the easiest way I can describe the period is if you imagine like a boat on the ocean, and let's say that there's waves that keep going by. As the waves go by the boat goes up, and then it comes back down. If you count how many seconds go by before it goes back up again, that's the period. So as the boat goes up and down in the waves, every time it goes up, it hits the top, and then it goes down, and you start counting, and then it goes up and hits the top again. The time difference, that's called the period. The bigger the period, the less severe the earthquake. A big period would mean the boat is going up and down, but it's taking a long time. If the boat was going like this, that means waves are going by the boat really fast, so it's going up and down a lot. Okay. So a longer period is better. That means the waves aren't coming from the earthquake as often. And the last factor that affects the earthquake is B, which is some type of factor that accounts for the weakening of the wave. And I would think that has to do with the kind of material that the earthquake is traveling through. Right? Think about what happens if you drop like a huge boulder in the middle of a pond, right? Creates a huge wave, and that wave spreads. Then think about what happens if you take a huge boulder and drop it in like a giant pile of sand. Well, you'll get a wave, but because the sand it's kind of loose, it kind of absorbs the energy, and it's probably not going to travel like it would if you dropped it in a lake. So that accounts for that kind of stuff. All right, so basically you just take those three variables and you fill them into your formula, and that gives you the intensity of the earthquake. All right, so let's try an example. All right, so this is example 5. So find the intensity. So let's say A is 400. So that's how much the ground is moving in micrometers, 400 ohm. All right. What's the next thing? We need T. Is capital or lowercase? Lowercase. T is how often the waves are basically like hitting you from the earthquake. So let's say that the waves are coming every 3 seconds. Every 3 seconds another wave comes by from the earthquake. And B, that's a factor that accounts for the wave weakening. Let's say, I don't know, 4.3. Okay, so find the intensity of the earthquake. Okay, first, can someone remind me what's the formula without anything plugged in? Or, yeah, Ilya.
R equals log A T plus B.
Plus B. Okay, so let's fill that in. So log of A is 400. T is 3. And how much is B? 4.3. Okay, so let's see what we get. We don't want to round any of that till the very end, so just type it all in exactly the way you see it on the board. So log of 400 divided by 3 plus 4.3. Okay, so that would be a magnitude 6.4 earthquake. Okay, magnitude 6.4. That's the homework for tonight. Just on 3 over. So 1, 5, 8 through 10, 16, 23, 25, 28, 42, and 52.